It's a pleasure to welcome here César Rodríguez Rosario from Strangeworks, which is a startup based in the US, where what they do is have well, I'm sure he'll tell us all about this, but they have an online web platform for quantum computing, where you can try different languages and even like share exercise, share programs, etc. So today we'll have a short tutorial, which will also be an introduction to quantum computing, right? So I keep saying that this is a course about quantum physics, but today you actually get a bit of quantum computing. Okay, and this will be on YouTube, but for some things it's better to do it live because then we can help you a bit during the tutorial. So go ahead, César.
So, hi everyone, I'm César. So I'm currently the chief scientific officer at Strangeworks. I consider myself a physicist, but back in the day I used to be a software engineer many months ago, and I decided to start physics because I wanted to program quantum computers, and all the professors I knew told me I was completely crazy about it. And so many years after, now I'm doing it finally. Yes, and so Lídia asked me to give an introductory tutorial. It's going to be an introduction to quantum computing in general with some hands-on examples. And so I ask you to ask questions. You can interrupt and so on as needed. And let's see, how many people do we have? I cannot see. Oh yeah, I see 8 participants. Okay, yeah. So the group is not so big, so feel free to interrupt and ask questions and so on. This is intended to be very hands-on, simple experience of coding some basic things for quantum computers. Okay, with that said, I'm gonna get started with the center. Okay. Yeah, so quantum computing is now. This is sort of my main message today. Quantum computing is the biggest revolution in computing since computing was invented. But quantum is quite old in some ways. Quantum is our reality, it's what the universe is made of, and so on. Quantum seems very strange. I'm sure you heard many uses of the word, and it seems very esoteric. But this is really not true. Like, the world is made of quantum. We just have the wrong perception about it. We have a very limited perception about it. And so the people that quantum is not strange, it's just us that are wrong about it. And this is because our brains are excellent at thinking about classical information. Classical information, zeros and ones, bits, that is only a tiny part of if these are bits, this is sort of quantum information. It's much bigger than that. And quantum computing really is about using the rest to compute. It's really that simple. Instead of just zeros, why don't you use the rest that we've been ignoring all along? Today, I will answer the 5 most important questions in quantum. So you can follow along. It's going to be, what is quantum? Why is quantum? Where is quantum? Who is quantum? And when is quantum? So this is going to be roughly like the outline of my talk. What is quantum information? Why is quantum computing so powerful? Where to do quantum computing? Who is a quantum developer, and when is the right time to start? So, introduce quantum computer, I'm going to start just, they always say when teaching you have to start from the known to the unknown. So this is everything we know now. This is what we're used to with computer. These are classical computers. You can call it HPCs. You can call it tensor processing units, graphical processing units, field programmable arrays, the laptop, the tablet, my phone. These are all essentially the same computer in these terms. However, there are some limitations to them, and these are seen more and more nowadays. And they happen for some problems. And it's that for some problems, the data complexity grows so fast that we cannot, the classical computers cannot keep up. These problems are usually problems that you add one additional data point, and then suddenly calculating the problem is hard. Then you add one more, and it becomes way harder. It doesn't come like twice as hard, and so on and so on. And these are common problems, like in network problems, in chemistry problems. When you add one electron, it becomes very complex. So these are things that our existing computers are not very good, and we are so eager to compute these problems because they're so important that we can be pretty confident they'll never be good enough. Like even if they keep, even if we assume exponential growth, our desire is fast, it grows faster than that. So these are fundamental limitations of classical computers. Okay, so quantum, it's an entirely new way of computer, and we're just at the very beginning. You're starting to see the potential of it. These are very early stages. So when people tell you that in next year we're going to have applications in the enterprise and so on, don't believe them. This is really not true. This is a very early dev industry. But what I do want to give you is fundamentally different than everything we do. This is way more different than machine learning, way more different than AI. Those things are still classical computer. This is a completely different beast. And often people ask me, like, how much faster is quantum computer than a classical computer? And the answer is the question. And the way I explain it is that it's like comparing a train to an airplane. So yes, airplanes are faster than trains, but some trains can be actually faster than some airplanes. You know, there's some small ones, and it's missing the point, because the point is the airplane takes you to a place you couldn't go with a train. That is the main point. And of course, you use them in combination. You go to the airport on the train, and then you take the plane to Japan, let's say. And so this speaks to how different classical and quantum computing is, and how they're not independent from each other. Quantum's not gonna replace classical computer. They're complementary and they're very different. And you do not take the airplane for very short trips, for example. You take it for longer trips. And this is the same for quantum. You use it for very specific. They're better at those tasks. So a lot of people want to know, when is this quantum happening and so on. And the pessimists say in 20 years, some people say it will never happen. Quantum computers will never exist. There are some people that say that. I think they're completely wrong about that. That is never going to happen. I think we have already enough proof of concept, and there has been some design basically to say this will happen. And the optimists think it's going to happen in 3 years. This you will see this often in all the business magazines. They say, oh, it's coming, it's here. And I will say that what you have to do is you have to prepare today by taking courses such as this one. This is really important. It's going to be way different than the internet came and there were no HTML programmers. This is you need a lot more training to understand quantum computing than you need to program a web page when the internet started. So there's going to be a bottleneck of people. There's going to be a bottleneck and we have to start preparing today by taking these courses, by learning, by being exposed to technology, by testing the technology, because now it's very, very early. So the major applications for the major areas of impact in quantum computing is pharmaceutical materials. I really think this is one that's going to benefit the most because quantum computers are inherently really, really good at modeling quantum systems. And molecules, after all, are just quantum systems. And the reason is very simple, is that a quantum system, a molecule is very complicated. This is how we do it now. We take the molecules, the real molecules, very complicated quantum mechanical object. Then we do a lot of approximation and we cut a lot of stuff and we treat it as a classical problem. Then you take this classical problem now and you use a classical computer to calculate things on it. And it's really, really hard. So at some point you do more approximation and you stop. And then you take this and translate it into the quantum solution. And in this process, it's very long. Quantum computer, you can just take the quantum problem and put it in a quantum computer and you're done, like direct mapping. And so this is going to change how we do materials. This is going to be how we do medicines, in the sense that right now, all these things, they involve a lot of people with lab coats in front of lab benches and so on, doing trial and error. And of course, if we can calculate the energies of these big molecules, we could cut down a lot of this trial and error to make it more efficient. There's impact also in optimization. That speaks and logistics. All these things go very, very tightly together. And in data science, it's gonna be very disruptive. In cryptography already, it's being very disruptive. That is that the system, we know that the existing ways we do cryptography, that is to secure the sum shard, they're gonna be outdated already. Like people are moving towards new ones that are secure against quantum computers and also quantum secure. Quantum search is very powerful. I think I might have a little time to speak about it later. And this is, searching on a Google database and so on. It's going to be much faster. And machine learning, this is a very really broad area of interest. There's quantum. So The main things with the main challenges to get started in quantum is that there's limited access. Quantum computers are easy or cheap to get to, and simulators also are very cumbersome in the sense that this is so early that things are changing so fast that you break compatibility. You get that darn simulator running with the software, and 2 weeks later do an update, and who cares, because the previous example don't work. The second challenge is there's not a lot of people, because you need people with different expertise, from quantum physicists to engineers to developers to people that understand the problems quantum will be applied to, and all these have to have different understandings of quantum is, but they have to be able to talk to each other. And finally, is that this is a very long-term play. Like I say, this is not a trip to Puerto Rico. This is a trip to Mars, and everybody should be very very conscious of it. So what we're trying to work in our company is how to address these things. Is we're doing it by making it easy to access quantum computers and simulator, making it easy to collaborate, which is what we're going to be doing today in the class, and also make it easy to have different entry points for people from different disciplines, and so you can get started. So I encourage you to go to quantumcomputing.com/ETH, and there you will see. Let me show you the screen. So this is the quantumcomputing.com and ETH. So this is how it looks. And you can see here Strangeworks tutorial. Click here. And please leave this browser open. It's very, very important. You can sign up if you haven't created an account. Go sign up here. You have to authenticate an email. So I want you to start doing it early, so when we actually have to do some live coding, you're ready for it. And I'm going to be referring to these examples in order. These are the links that you can use later to do them. So please keep this in mind and refer to it. Okay, so let's go back to the talk as you guys start to sign up. So a big question I always get is where do you get started with quantum computer? There's so many options, and what we're trying to do really is make one-stop place that everybody can go and start playing with all these new tools without all the headaches of installing them. Okay, so now this is the main portion of my talk, and I like to call it like "Hello World, Hacking Quantum Today." And of course, notice this funny bracket notation. And this is to signify already it's going to be the quantum introduction. And the first thing I want to do is dispel all the myths a lot of myths that are out there. If your interest in quantum computing comes only from headlines from newspapers, you will find out that every day there's a new headline. Oh, they make this gigantic breakthrough and everything is solved now. They make exceedingly large claims and so on. And it seems like, oh my God, the world is transformed tomorrow. And the truth is that is not where we are. We are at a very early experimentation, exploratory stage in the industry. And to highlight this, I want to just give you an overview of all the hardware that there are there. These are just 4. There's more, by the way. I think this is D-Wave, Rigetti, Google, and IBM's. Some of their quantum computers. There are many. And there's more companies I just didn't put here. And these are the images that you get when you Google quantum computers on Google search. And these are some of them. And you will see them over and over and over reused on every news article about quantum computers. The funny thing is that these things look super cool. They look steampunkish. I love it. I love steampunk. But these are not the computers. These are actually the cooling systems of the computer. So this is kind of like you say, oh, let's see that Intel microchip, and then you take a picture of the fan in the computer. That is really what we're seeing, because it's kind of cool. You see the chip here; it looks kind of normal here. You can see a little bit of it. But another thing I want you to notice is how overloaded these things are. And this is because quantum computers, to keep this quantum information very, very robust, we have to cool them at extremely low temperatures. And a lot of the difficulties are how to engineer these cooling systems so we can access everything and keep it very, very, very cool, independently, all these things. So this is already, you can see just from the pictures, what are the challenges on it. And ideally, when we have quantum computers that are mature enough, we want computers that can have a lot of qubits. Qubits is the quantum diagonalization of bits. That these qubits are very well connected to each other, so you can address them. And that the qubits, you can rely on them, you can trust them, you can do operations on them. You want all 3. If one of these companies figure out a way to do all these 3 consistently and grow, we will say that we have scalability. And that's when the industry is going to be boom. Now we know where we are. Now we know how fast this can grow because we can scale them. Nobody has figured that out. This is the truth. And what all these companies are doing is they're taking different compromises on these three axes. They cannot do all three. So the other, for example, if you cannot connect all the qubits as you like, you can sacrifice some qubits to have them connected. Like, if you have 1, 2, 3, and maybe 1 and 3 cannot speak to each other, but you can use the 2 as a mediator between them. Another one is you can sacrifice reliability of qubits by spending qubits and this is known as error correction. This is when you have several qubits supporting just one qubit information, this kind of thing. And you can do these compromises. And all these companies, basically what they're doing is they're just taking different compromises and trying to push with their technology how far they can go with it. And this reminds me of these human towers that people do. You see, like, they're all clearly human towers. They have very, very different strategies, and they might be good for different things. This one I find very impressive. The one with this family with a little kid and so on. But this clearly is not very scalable, right? Like, you cannot imagine a picture of 50 people on top of each other. This one here, it's exceedingly complex and super cool looking. This one seems to have like some strategy going for it. And this is really what you should think about. Like, they're just trying to figure out ways such that at some point we can keep growing these towers consistently in time. So this is an overview of the hardware. Now, an overview of some of the software tools. By the way, there's a lot more, but these are some of the bigger ones. And so we have three main categories, and we have three and some others. So the first one is the pink one is the Python flavors, and there's some other Python flavors, by the way. One is IBM Qiskit. Well, one's Zurich by Google, and then one's PikeWheel by Rigetti. And these three, they're Python with a little more to the quantum stuff. All these three speak QASM, which is a quantum assembly language. That's how they call it. I don't like that word because assembly languages are a little bit lower than that, but a different level than that. But this is really another way to program quantum computers. And then you have high-level languages like Q#, and some others. And there's a lot more, like right at ETH, you have Project Q and so on. There's a lot of languages, so on. The truth is, all these languages are changing very fast. And if you go to Google search page, I think one of the first or second line, they say, we will break compatibility, which is a big headache. And IBM, if you go look at all the examples, they have tons of examples spread all over the internet. And most of them don't work with the newest version. Like, this is because things are changing super fast. This is how early we are. So there's a lot of pain points in this. There's complex installation, dependency management, updated compatibility, and then sharing code because of these issues. And we hope with the quantumcomputing.com, which is a community, free community version to give access to all these tools, we take out the headaches so you guys can just play with the quantum. And with that said, I really believe that the best learn to learn quantum right now, since we have access to computer, is by programming quantum computers, by playing with quantum code. And so this is what the main part of my talk is gonna be about. And if you don't understand all the details, don't worry about it too much. This is more, I want you to later go play with the same examples again and again. A lot of them require a lot of trial and error, and that's fine. I just want you to take away the fear that, oh my God, this is very hard and not try anything. This is really as simple as coding. So if you haven't done it, please go to quantumcomputing.com/ETH. Has everybody got access, or anybody has problems with access? Let's see if anybody has problems with access. No. Okay.
Can you see how many people signed up?
I can, but it's gonna take me a while because that's privacy information. I shouldn't show to everybody. Yeah. No, so, but if unless somebody protests, it's not. Please try, and I strongly encourage you to try it and play along because this is how it's intended. Okay, so now let's start with the first quantum concept. This is quantum superposition. Lídia, have you introduced quantum superposition in class already? I guess so, right?
Yes.
Okay, yes. Yeah. So since she has done it, she's done all the hard work. I'm gonna just give you a visual analogy, and as all analogies is terribly limited and flawed, and that's okay. And so the way I like to think about quantum superposition is that I told you the quantum world is bigger than the classical world, and we are used to thinking in the classical world, which is insufficient to see everything else. This is why it's puzzling, and the puzzle is not on the quantum, we're just not made for that. And this reminds me of when one tries to take a 3D object in a 2D plane. The 2D plane is fundamentally limited to capture everything about the 3D object. It just doesn't have enough. And this is the same when we try to look at the quantum world with our classical mind. We're very limited in this sense, and we cannot. And so we're missing some of these things. So I'm trying to signal this by this wireframe here. This is of course a representation of a 3D object in a 2D plane. However, I'm sure you have seen this perspective effect. When you look at it, sometimes these 3D objects, your brain constructed thinks it's a cube, like a box. And sometimes it thinks like it's like a corner, like it's inverted. And it sometimes messes with your head, and it just like if you can even get your headache if you have like a tiling of this. And this is similar, and this is similar to a quantum measurement in the sense that we have this information when we try to look at it, even though there was a quantum superposition, something that's much bigger than the classical world, we only see one version of it or the other, but we do not see the complexity of the quantum superposition. And although it's all encoded right here inside. So this is just an analogy, by the way. You cannot do qubits with these boxes. It's a limitation. You can actually do QDITs with boxes, by the way, Lídia, but not qubits. There's a fundamental limitation to it. Yeah. So now to start playing with qubits, I encourage you to go to the Play with One Qubit project. I'm gonna show you how to do that. So there are two ways to do it. You can click here, Play with One Qubit in the ETH webpage. You can click Add this project, and you can click Submit, and you will have the project in your account. The alternative way is you go to the project library and just find it here. They're in both places. You add this project, submit, and you will have the project in your account. This is the sort of this is the README file, so this is sort of the documentation. But if you want to see the code, just click here for the main.casm. This is called in QASM. QASM is the Open Quantum Assembly language. A lot of the programs I mentioned write to QASM. So this is like it's a lower level language. I'm using this for teaching because all the others, if you understand some basics of it, the other ones make sense. And also because it doesn't have all the complexities of a full programming languages, but it has all the complexities of what you need to do with quantum, which is what I want to focus on today. So now the main things is, they have the standard introductory stuff, QASM 2.0, include libraries and so on. Then you create one qubit. This is a quantum register, so for one qubit. And then you create one classical bit. So this is always, you want to do an operation in one qubit, and then you want to measure it, so you have the classical bit to store the information. These are some quantum gates that I will explain to them what they are in a second. Some just random ones, just some of the quantum gates. Feel free to start playing and commenting, deleting. This is copy paste. Try them a few times. This is really what I wanted to do. Okay, and then there's a barrier. This is just to make things look pretty. I will show you now in a second. And then you have a measurement. So now let me go back to the deck. Okay, so qubits are of course two-level quantum mechanical systems. You can have quantum superpositions, and you do measurements on them to find out the outcomes. And there's many gates. And today what we're going to do is just play with some of those gates. This is really the only purpose of this example, is that you get to say, woohoo, I control my first qubit. So some of the gates, if you can represent the qubit as a sphere, the block sphere. This is only true for one, by the way. The two qubits you cannot represent by by a hyperdimensional sphere. But it works for one, so we're going to use it. So now imagine if this arrow here is your quantum state or your qubit. If it was pointing up, it would be 1. If it was pointing down, it would be 0. Everywhere else is a superposition. And then you can do rotations on it. This is how an X rotation looks like. And a rotation on the X-axis is done by this matrix. You can do Y rotations around the Y-axis. You can do a Z rotation on the Z-axis, Z-axis. And finally, this is a Hadamard rotation, which it does two rotations around one half rotation, then another another rotation on another axis here. This is a complicated one. And these are the most common ones, by the way. These are not the unique ones that you need, but these are the common ones. Oh, but one person asked me, like, why is the Hadamard gate so weird? What does it do to? And I found like a good analogy, which is it's a bit similar like when you're playing in the shower and you increase the heat, and then you increase the coldness, but then to increase the pressure, but then it's too hot, so you have to start playing with it. It is similar to that in that sense. Like you have to like play with two knobs to get things just right. Okay, so now here are some qubits. Here are some gates. You can see I have all the basic ones I showed. They're here. You can try a bunch. And there's some additional ones here I didn't even mention, and that's okay. You can go look at the documentation, start playing with them. This is fine. I just want you to feel like you control your first qubit. When you can just take the program, you can run the code, and here you have to type the number of iterations. This is the number of iterations because remember that the outcome of the measurement is probabilistic. So we need to take a lot of measurements to have a sense of what's going on. It's like the outcome of a flip coin. You have to flip the coin many times to know if the coin is fair or rigged. So I recommend you do like 10 or something for this example. 10 is a good one. You can do 100, but it takes longer. So I think 10 is enough for this. I science program for 10. Then you can click run, and this is actually running the quantum code in a quantum simulator right now. So let me show you what I have here. So we use QASM. This was run in the QUBIT simulator. So it's a simulator provided by IBM that we are hosting ourselves as Strangeworks. And so what this already, the important things here shows how many shots. This was the number of iterations that we did, how many times we ran the program. And this is how the circuit looks like. I had the Hadamard gate and the Y rotation gate. Then I had this barrier. The barrier is just so it looks nice. There's no other reason for it. It's just so because otherwise sometimes I like to optimize some things and it doesn't look so pretty. And then this is a quantum measurement on the qubit, and then it stores the information on the classical bit. And then here we can find out what the outcome was. You can see the outcome as measured from this qubit to this classical bit was 30% of the time it was a 0, and 70% of the time it was a 1. So I encourage you to now go try and maybe add some other things. Let's see. Look, if I add this line, you can copy, paste, and so on. Running again, and just try a few things so you can see that you are indeed controlling a qubit. Of course, to understand how to control the qubit, you have to play a lot with it, understand the gates, and so on. But you see now I changed the program a little bit. I added another gate, and things are a little bit different now. It's like much lower here and so on. So please start playing around a bit. Just delete some lines, comment some others, add some others. Okay, let's see here. Do 10. You see this one was 100% all the time. So I just want you to just start now. Now I have 100%. I can do some funny things with this. Let's see. Okay, I'm gonna put this one here at the end. Just start playing around, just so you feel like even if you do not understand exactly what it's doing, you know that you are controlling a qubit in a simulator, of course. Like this is not hardware access on this one. Yeah. So now I made it 0, 100%. So just start playing with it for a minute or so. Does anybody has any questions on that example? If not, I can continue with the next one.
Yeah, one example, just question, sorry.
Yeah.
I was wondering, the qubits, they're always initialized in the ground state, right?
That is correct. That is correct. That is correct. Yeah, that is correct. This is a convention, where most computers assume that the qubit is always on the ground state, and a lot of the work of the programming is okay. Everybody starts in the ground states. How do I want to initialize them myself? Like this is seen as the job of a programmer. It's kind of like setting the right label, the value of a variable. So you have to say, okay, now I want them all up. So this exercise of controlling qubits, it's really about that. It's really about how do you initialize single qubits to whatever you want it to be for the specifics. Yeah.
Okay, thank you.
Yeah. And there's very good reasons why people choose 0, and it's that because these quantum computers are very error prone and have a lot of problems. Then what they do is there's always like one state that's when everything goes to hell, it goes there, and so you can count on that one. then they call it 0. That's really what they do. Like, and so they just call it 0. Okay. So that was they're very confident. That's a good one, and they always decide it to be 0. And of course, a lot of subtleties on this. Then you can have there's representations of what is the 0 in the hardware versus there's 0 in the representation of the hardware, and there's some mappings, and there's a lot of tricks, and there's a lot of layers between it. But for now, assume everything is initialized to 0 by default. That's the convention. Yeah. Okay. Any other questions? Because we're gonna go now. If not, we're gonna go to another 1 qubit example that's a little more interesting. So feel free to ask before we go to that one. Okay. No. All right. So I'm gonna go to the next example. Okay. So. Here. So now there's this other example that I called solve this Rubik's sphere. I'm sure you find it on the links, or if not in the library. And this is a terrible pun. Of course, everybody knows the Rubik's cube, right? This puzzle. And so I'm writing with a Q, and it's because it's the block sphere. It's not a cube, it's a sphere. But it should remind you of a very, very simple version of a puzzle like this, where you have to rotate things to get things where you want them to be. So this example, this is a little challenge. That is that's for that. So the problem is as follows. If you have open the code there, you're gonna see like a big wall of code. I'm gonna go through that in a second. But the setup is like this. I took 1 qubit that was in the ground state, as I said, they also in the ground state, and then I rotated around in a lot of complicated ways. I tried to do it such like you cannot see what I'm doing. Like, so that's why it's convoluted on purpose. If you like matrix multiplication and so on, you can sit down and calculate it. That's perfectly fine. That's one way. It'll take you much longer though, so I do not recommend it. I try to make it hard. I try to make it such that you will not want to do the lovely matrix multiplication. So I moved the qubit to some point that's not the ground state. And your mission is to move this qubit to the ground state, to control it to a well-defined state. So you have to undo the scrambling essentially. And so for that, let me show you here what I'm talking about. Okay, so in the tutorial, you can go to solve this Rubik's sphere at this project. Okay, so I'm gonna go to the code, and you see that this is the standard initialization like before, the first few lines. This is the scrambling. So this is if you really, really love multiplying unitary matrix, knock yourself out here. I suggest you don't do it. And now this is the things that you could do to unscramble it. So these are suggested operations. These are suggested rotations that you can do to unscramble it. So, but before I try any, I just want to run it. And I suggest you do about 10 iterations for this. I designed it so it won't be too much. You can do more, but then it takes a bit longer and you don't get anything more useful. Less than 10, like you get statistical errors that might not be helping you much. So you see, this is how it looks like the comprised operation. It's a complete mess. It's on purpose, so I wanted to make it hard to see. Okay, and then we measure it and it goes to 0. And this says it's about 60% 1 and 40% 0. So your goal is to make it 100% 0. This is really the goal of this task. And the way you do it is like I have some things here. You can comment one line, you can comment another line, and let's see, I commented 1, and you run it. You see, that did a little something, but maybe not enough. Okay, so maybe you take another one, maybe you try a different one, and so on. And there's many gates. You should try several of these gates and play with it. So I'm gonna give you guys 1 minute to start playing with it. I recommend you do between 10 and 100 iterations for this. And so please play with it. And then in a minute or so, I'm gonna give you some hints. And by the way, if any one of you figures it out, then I want you to please say, hey, I got just, like raise your hand here, like just tell me, oh, I got it. And then you can go to here, share the code for the solution, make this project public, okay? Or actually here, write César as Strangeworks. This is the best way to do it. So, And if you do that, you will allow me to see your code, and I can run it. I can grade it for you. I can check that it was done properly. So that this is also a way to do it. But tell me also here. So if somebody does it, that's fine. And if you don't get it right away, that's okay. I hope you guys will play more and more with it. Okay. So let's see. Okay. Perfect. Mm-hmm. Okay, so while you guys are at it there is some hints. Of course, I already said try about 10 iterations. You can do more, but 10 is about right. The more you do, the longer it takes to try and error. And I gave you there a lot of possible gates. You can do it just with a combination of X, Y, Z, and Hadamard. Just those are enough to do it. Otherwise, the problem is actually quite hard. Like to try for every possible, it's actually really, really hard. So I suggest that if you try just with those, you'll find a solution. Then the other tip is that the order of the gates matter. This is really, really important. If you do Z and Z and then H, it's different than if you do H and like these things like that. So just play around, try one and try the other. And the final one is you actually only need just 2 of these gates in the right order. So there's not so many combinations for you to try. So, it's this 4 in groups, so try them 2 by 2, both orders, see if somebody gets it. And if somebody gets it, please let us know in the chat or so. Yeah. So again, it will be one of these 4. It'll be 2 of these 4. Yeah. Okay. Two of these 4 in some order, and then it should work.
There's 2 people who say they have a solution with 1 gate.
Great. Awesome. Yes, great. Yeah, perfect. Single gate. Try, if you got a single gate, try increasing the number of iterations. So for example, let me undo this here. So when you do iteration, if you just happen to click just 1, then it's like flipping a coin once, and then yes, sometimes you get heads just by luck. So try about 10 or more. Like if you wanna, just to be sure, it has to pass the test for many times, so you're pretty confident. So try that. Yeah. Okay. So 500 is 500 gates. Single gate. It could be. It depends on which gate do you use. And by the way, this is not unique. This is something very, very important. The solution is not unique, and it's okay. This problem is designed that way. Do not tell me which gate do you use. Just click here, share, and write and send it here, and I'll check it out later just to see what was the creative solution that you used. But I do think I did add other gates, so don't say it here because I don't want it to be spoiled by anybody else. Yeah. Okay. Yeah. Okay. So I think several people did it, and if you haven't got it, that's fine. Just keep playing with these things. This is just to give you the sense that you were able to control your first qubit to do a task. This is, of course, a silly task. A qubit is not enough to do anything meaningful, but at least you had like a goal and you reached it. So just play around and then feel free to share your solutions with me. Okay, so now for the next example is about quantum entanglement. It's to create quantum entanglement. And you will find the project is called For Whom the Bell Entangles. And I want to just give you again, just take this analogy, push it a little further to remind you of what entanglement is. So I told you a qubit was like a 3-dimensional object, and we just happen to represent it in 2D space, so it's feels a little odd. And when you look at it, sometimes you see a box, sometimes you see like a corner in this analogy. Well, if you put 2 next to each other and they are entangled, their entanglement is a quantum correlation that is really, really, really strong in a way you couldn't reproduce anything like this in the classical world. And this is like everybody, if you read any article, I say what Einstein's called spooky action at a distance, blah, 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 blah. Well, the truth is Einstein didn't get it. And Einstein like that a long time ago. And now many of us, this is what we do for a living. This is not so spooky for us. We entangle things for a living. This is very, very important. So I was like, oh, come on. He said that in 1930. We have quantum computers now. Like, give us a break. Entanglement is not so spooky. It's something that we do. But what's funny about it is that if you, just like in this analogy, if your brain thinks this is a box, the next wireframe diamond, it sort of forces it to look like a box. Like they have to be kind of consistent. And if one looks like a corner, it forces the other to be a corner too. And so you can sense that if you measure one, there's some sort of, it determines what the other one is in some way. It could be this way, it could be that way. And this is to push the analogy a little further from before. And by the way, there's multiple ways to do entanglement. This is just what I wanted to share. There's just multiple ways to do entanglement that are consistent. So what we're gonna do in this example for whom the bell entangles is to introduce a new gate, which is the control node gate. It's a 2-qubit gate, and so and the 2-qubit gate it can flip a qubit depending on the value of the other one. And this is a very important 2-qubit gate. Of course, you cannot do computations with single qubits. You have to start doing things between them. And another reason why I introduced this one is that because it's the essential one to create entanglement. And in fact, if you look at any quantum circuit for anything, you'll see at the very beginning, there's always like a big thing that looks exactly like this Hadamard gate and this control gate. This is because for using quantum computers to its maximum potential, you always have to take and create some entanglement for it. If a quantum computer cannot create entanglement, it's not a quantum computer. We think quantum computers span entanglement to get this speed up, to do things better. So we prepare a qubit in the Hadamard gate, then we prepare 2 qubits together with the control node, and then we do some quantum measurements. So things to try. So I'm gonna show you here in the code how that looks like. This is from the bell entangles here. See, I have a small explanation of this. And let's go to the code. Yeah. So this is the code that generates that circuit. And I wanted to run it. I wanted to run it at this stage just once. Yeah, for this one, I suggest you run it just once. And the reason is, you see, you get 1, 1 in this case. Now let's run it another time. You see? I got again another time, and if you keep doing it, you will see you only get some of the combinations between them. I'm gonna do 10 now to showcase this better. But you see, I'm getting either 0 zeros or 1 1s always, and you can actually look, and you see there's nothing else except these. Yeah, and if you try 100, you will see that no matter what you do, you only get those 2. This is because you have a very special entangled gate that creates entanglement between the states in this 0 zeros and 1 1 cases. So by doing this, you have created your quantum entanglement. Remember, this is what Einstein didn't like at all, and now you can do it. You see, so it wasn't so spooky after all. And so while we are at that, what I want you to do is go to the code and change this Hadamard gate for some of the others that we learned. You know, the X, the Y, and such, and just see what happens with it. You're gonna see that the levels of 0 zeros and 1 1 is gonna change, and maybe some other things will change. And another thing you can do, if you really, really wanna play with it and try to break things, is you can add crazy gates here. You can add a X here or a Y here before. Now you know the code a bit, so feel free to play with it. And what this will do is you can either create things that are not so entangled, or you can create things that have different kinds of entanglement, and that is fine. This is like, I just want to give you a sense of that you can play with this and create entanglement on your own. So for example, you see this the Hadamard. If you want to have another one, let's say you can do the X and see what happens after, let's say, 10 iterations or so. So this one didn't change anything. I mean, actually, it did change something. Now you have 1 1 all the time, right? There's no entanglement here. and between 0, because before we had entanglement in 0, 0 and 1, 1. Now there's just these correlations. So start playing with this. You can, if you want to really mess things up, you can add more lines here. Let's say if I want to change, I'm gonna put this back to X, to Hadamard. Okay. Now I'm gonna do a rotation on the X. And so let's see here, run this. So you see I'm starting to add gates here, and I'm messing things up a bit. So I just want you to play with it so you feel that you manipulate some entanglement, because that is the minimum one needs to do something useful with a quantum computer. Okay, so are there any questions at this point? Okay, no. So now we're gonna go to now a big part of the talk, which is where I actually explain you why quantum computers are so powerful, and we do something that's a little more powerful than a classical computer. So I think please stick along. There's gonna be a little more theory. It's gonna be less, but at the end we're gonna go back to the example. It's like we have to build several blocks to get to it. So this is the part I call the power of a quantum algorithm. And the purpose of this is that you end up with a little feeling of why quantum algorithms are fundamentally more powerful. I'm going to try to use no physics and no computational complexity arguments. This is a very visual way. And then after that, you're going to get to play a little bit with this very simple quantum algorithm in the Strangeworks platform. Okay, so the setup for this is, this was before lockdowns and all that. Imagine that you were at a bar and you walk out of the bathroom and you realize maybe you had a few drinks too many, and you're trying to look for your friend sitting at the bar, but everybody has the same T-shirt from the local band or the local football club. Everybody looks kind of the same. It's that kind of bar where there's in black or something like that. And then you're gonna find your friend, so you start walking towards the bar. And as you walk, you realize like you're a little unsteady, and then you get very, very close, and you walk straight ahead, and you walk the first person you see, you try to look at it to see if they're your friend, and maybe you got a little too close to them, and you're like, it's not my friend. Okay, then you take a step to the left, and you look at the next person, and you get too close. It's not my friend. And like, okay. Then you take a step to the right because you're drunk. You don't remember you already annoyed this person. And then you look at them again too close. It's not my friend. And so on and so forth. You're like looking for your friend in this very inefficient way because you're drunk. Until you find your friend. This is an option. But the most likely option is that they call security on you and ask you to please leave because you're bothering all the customers. So how will you model this mathematically? Of course, this is what everybody here cares for. It's like, how do we model this mathematically? This is a very complex drunken behavior, and we can model it in a very, very simple way, which is with some randomness. Although the drunk is doing something very complicated, if we assume that each step to the left or the right is taken randomly, like flipping a coin, and if he has heads, you take a step to the left. He has right, you take a step to the right. In each step, it's random, and then random again and random again. But there will be some simple way to model this and so on. So even though the drunken behavior is complex, we can model it by assuming it is random. And here's one way to do it. So imagine here, this is a security guy here. And one day you do this random walk, and then security guy finds you in this spot at the bar. And then they ask you to please leave. And then the second day, the security guy finds you here instead. And the security guy, by the way, he realized statistical physics, so he started to keep track of everything you're doing. And then after many, many, many days, he has been keeping track of everywhere he has found you. And the security guy / part-time statistical physicist, he can reach two conclusions from this. One is that you have a drinking problem, and two is that you follow the Bell distribution. And this is very, very fundamental. The Bell distribution, the Gaussian distribution, this is like IQ, all this up. There's all these measures that we think is very, very fundamental. And in fact, it's so fundamental. Like I can show you how to do it. I have here, it's called a Galton board. It's actually the pegs exactly like there. I'm gonna flip it around and throw a bunch of them. And you see, it roughly follows the Bell distribution and so on. So this is really, really very common phenomenon. Okay, so now what's important about the Bell distribution, the only thing I want you to think about is how fat it is, how wide it is. This is the standard deviation. And standard deviation is a way to describe how spread out this is. So for the Bell distribution, for this kind of random walk, this drunken walk, after n steps, we know that the fatness goes as square root of n. So if you took 9 steps, the fatness of the Bell distribution is 3. If you took 100 steps, the fatness is 10, and so on and so forth. Like the fatness of the curve goes as a square root of the number of positions. Okay, but of course we're doing here quantum computing. So let's get quantum drunk here. So we're gonna do the same procedure as before, but instead of flipping a coin, we're gonna have a qubit that allows for superpositions. So that means if there's a superposition, if it's 1, you go to 1, you go to 1. If it's 0, you go to the other side. And if it's a superposition, then you go to both simultaneously. You get into a superposition like this. So the drunkard is going into superpositions of himself as he's looking for this. So how would this look like? At each step, they go into a superposition, but when the security guy comes to look, he will only find it in one place with some probability. Maybe next time he finds it in another, and so on. And of course, our security/statistical physics friend, he's keeping tabs on where he finds you. And he will find something very, very curious. If you were walking quantum drunk, the distribution is really different. This is not the Bell distribution. And this is really, really, really fundamental. So again, just to summarize, if you're classical drunk, it will look like this, like a Bell distribution. And the fatness is square root of n. So this is like a Bell, so you're on a Bell. And then this is the quantum drunk. You see, this is a really complicated distribution. This has to do with quantum interference, negative destructive interference, positive interference, and so on. I like to think of just like a vampire fangs on like wolf teeth or something distribution. Bell is a nice name. This one doesn't have a nice one that's memorable visually, and it's very jagged. And this is very, very important. This means that it's very hard to find the drunk at this low spots. He's probably not there. He's very likely around here. So there's like steps that you don't find it. You don't have to look everywhere. The main thing is like, look, the classical drunk tended to be close to the center. So if the security guy was going to start looking around the center is a good idea. But the quantum drunk is actually not so much at the center. It's way, way more spread out. And this is a really fundamental thing about quantum computing. And then this is so spread out actually that the standard deviation, that fatness, is n instead of square root of n. That means that the quantum drunk tends to be square times farther away than the classical drunk. He's a harder to find friend. It's much, much harder to find if you're looking for them because they're more spread out. And this idea between the square root of n and n, how this is square times faster, and this is underneath all quantum computation. I want you to think always this square times. This is a very fundamental thing in quantum computing. Okay, so now let's put the drunks to do something useful. We do the same drunk in this labyrinth here. So the labyrinth is called a glue tree, and every step it sort of splits up into 2 options they can go. But then at the middle is a little scramble, you see? And then I put like another tree on the other side, and so they come back together. And the question is, how long does it take them to find the exit? That's really the question. We send it first the classical drunk, and you see he's he takes some time in the middle, and then finds the exit. Good for you, classical drunk. Then we do the same for the quantum drunk, and he goes into superpositions, and he still gets a bit stuck in the middle, but because he spreads out more, he doesn't stay there so much. Like he has a tendency to like squeeze out of this part of it. And this is true, by the way, only for this kind of labyrinth thing. Now let's but both made it to the end, so this is not very impressive. Let's start sending more and more drunks. and then see what happens from this. Okay, so after a lot of drunks, you can see that the quantum drunks tend to make it out faster than the classical drunks. You can see there's a lot of classical drunks still stuck here in the middle. Some quantum drunks still, you know, it's like it's not perfect, but you can actually show that the quantum drunk is exponentially better, like literally exponential, to make it out to the exit in this kind of labyrinth. And it has to do with this idea that I was telling you, that the quantumness is square times more spread out than the classical one. Now, there's two main things that you have to remember from this. This is important for all quantum algorithms. Everything a classical computer can do, a quantum computer can do square times faster, which is already pretty darn good. But there's a lot more than that. Square times, for some problems with some very, very specific structures, if you are really clever, you can turn the squareness into better. And like in this case, it's exponentially better. This doesn't happen for it's not exponentially better for all things. It's only for some, but that's okay, because there's some important problems that quantum is much, much better at. So a lot of all this, and these are of course the quantum algorithms that we know they have advantages over classical ones. Okay, so now with and one last thing is that this quantum works, they seem a little toy-like, but you can actually show that all ways to do quantum computation, they map to this kind of problem. They're not so useful actually for doing the computation, but I think they're help visually a lot to understand how it works. Okay, so let's go to the quantum walk 4 nodes example. So again, so we go here, and for this example, please add it to your list here. Okay, so now I'll show you what this example means. This is a really, really simple quantum walk. It's really toy-like, and the reason is because if I wanted to make it real with the glue tree and so on, it's actually quite big and it's actually quite slow in simulators. Remember, this is supposed to run a quantum computer, not a classical one. Also the circuit is really, really messy, so it's a bit difficult to play with it. So I kept it the toy version, the baby version. So in this one, the quantum drunk starts in the 0, 0 node. Then he could go to either 1, 0 or 0, 1, and then he can go to 1, 1, and that's it. And after this, there's no exit. So if you keep walking, you go back to it. So in here, there's 2 qubits. There's qubit 0 and qubit 1. This represents the nodes of this network. This represents where he is. Qubit 2 is that quantum coin that you're flipping. And this is just preparing the coin. This is creating a superposition. So you can do you can superpose the walker. Now this is what it looks to take a state. Remember, there's 2 control nets, 2 control nuts, and another gate in the middle. This is such that you want to change both of these things to take a step from 0, 0 to either 0, 1 and or 1, 0. And this is the way it was defined to do it. You see it's control on both, and this is kind of to reset the coin enough. And then at the end, you take some measurement to see what it is. So this is exactly what this code does here. You can see that the control, this is the preparing the coin. Then this is one step, as I explained. So let me run the code. Let's say I'm gonna do it 10 times or so. Okay, so this generates the circuit from before, exactly as I told you. And you can see now the quantum drunk went to 0, 1 and 1, 0 with equal probabilities. In fact, he is in a superposition of zeros and 1. Now, I want you to make this drunk walk a bit more. Then you can do it by taking, this is one step. You can copy it, make it take 2 steps. Now it's 2. Say, just run it. Let's do 10 again. So see, I made him take 2 steps, and now he's 100% of the time in 1, 1. So I want you to start playing with that and try a few things. So we changed it to 2, he made it to the end. Try 3 and see what happens. Try then 4, try 5, just see, you'll see that there's like some pattern to it. Start playing with this, run it a few times. After you do that, other things you can do is change the initial state. You know enough gates now that if you want to mess with the initialization of where the walker is, you can try to do that too. Another ways you can do is mess with the coin. Like make the coin unfair or unevenly balanced. You can do that by adding gates here instead of the H, adding all the gates here in the middle, like really messing with this. I want you guys to spend some time playing with this walker, see what it does, and you will see some patterns, you will see some repetitions, and just try to mess with it, because this is effectively you know, doing a complex, messing with a quantum algorithm to change what it does. Okay, are there any questions on the quantum walk? Remember, you will have access to the account later, by the way, so you can play with it all you want after. Yeah. Anyone? No? Okay, so if there's no questions for the quantum walk, as I told you, this was a very visual quantum algorithm that I find very useful, because it has all the minimum components one needs to understand where does the power of quantum comes from, and how does one use it. Now, I want to give you an overview of some real quantum algorithms, and my intention in this is that as you look for examples, so you play with examples in a library, you have a sense that there's actual application for this, and so you can play some more. So, okay, so all right, so now I'm going to give you an overview of how of many quantum algorithms, and for this I will introduce a series of how powerful things are. Okay, so everything you're familiar with as in computer programming will belongs to this idea of they're either it could be a laptop. These are programs that you could probably solve with a laptop or with the biggest HPC in the world. It doesn't matter. But these are fundamentally classical computers, and they're not different at all, even though they're super powerful now. That what Bill Gates was using back when he started writing QUBIT, BASIC, and so on. It is really that level of stuff. So this is the class of problems that you could solve with a computer from 1980 or with the strongest HPC. Like, they're all kind of in the same category. I know it sounds ridiculous, but this is all one class of problems that you have. So if you have this computer, these are problems you can have efficiently. That is, it won't take you insurmountable amount of time. And of course, we know a lot of them. Like, one clearly is Zoom. That's a problem that we're solving right now with a classical computer. Now, on the other end, we have problems that are exceedingly difficult to solve, and that we think they're that there's no real good way to do them otherwise. So these problems, one of them is called the traveling salesman problem. The traveling salesman problem is, imagine that you have many cities in a map, and you're selling something, and you want to visit each city to try to make sales there, but you don't want to repeat cities. You don't want because that's kind of wasteful. What is the optimal route to do this? And this is actually known to be an exceedingly hard problem. You have to try every possible route to know all of them. Otherwise, you will not know you found the best one. And so we think these kind of problems are so difficult that, well, of course, we can do it for small number of cities. But when the cities get really large, there's no computer that could solve it in any efficient time. And if you add one more city, it becomes way harder. This is really like what I want to capture. So this one, I'm not representing by Bill Gates. I'm representing by this character. This is from the DC universe. He's not a superhero. He's beyond superheroes, and he's a destiny of the endless. And he is the representation of the personification of destiny. And he sees all possible paths. He sees every possibility at every time. So if you have a computer that could do that, which we think there's good reason to think they will never exist, and then you can solve that problem efficiently all the time. But you have to have destiny of the endless levels of power. Now, let's start making things a bit more interesting. In the middle, let's fill out the middle. By the way, this is not a quantum computer. Quantum computers could not do what destiny of the endless does. This is a misconception that they could do that. They're not that powerful. They're pretty darn powerful. They're pretty good, but they don't get there. So now there's some problems like quantum search, quantum optimization, that with a quantum computer, you can get a square advantage. The square number I was telling you from before. So this means that if you would take Bill Gates, and this I'm representing by Batman. I'm using Batman because square times, actually in complexity theory, that's not so much, but it is way better. Like, you know, Bill Gates is a millionaire, Batman is a billionaire. Bill Gates is pretty smart, and he can put like, what he puts his heart off, he can do like some amazing things, Batman too. But we fundamentally believe that Bill Gates, who could never become Batman, right? Like they're still human. Batman has no superpowers, but there's no way he will be Batman. And so this is, although it's still within the realm, it's the same, it's not so far. We think with quantum computers, you can do, you know, this is like better than a human, but he's not superhuman. This is Batman. And there's some problems like searching are like that, and quantum optimization. So in searching, for example, if Bill Gates, it will take him 10 days to search in a list. 100 days to search in a list. It will take Batman 10 days only, with the access of a quantum computer, of course. And if there was a problem that it will take Bill Gates 100 seconds to solve, it will take Batman just 1,000 seconds. You know, this is what square times faster mean. So these are like the easy problems for quantum, the ones that are not so powerful, but are still pretty darn powerful. Just like Batman is definitely more powerful than Bill Gates. And then we have a lot of more in between, and I'm going to start fleshing them out. So at this end here are the strongest superpowered individual. This is everything I'm going to put in this box. This is quantum. This is what a quantum computer could do. These are the most powerful things a quantum computer could do. And I'm represented it by Wonder Woman and Superman, because they're right there at like top superheroes. By the way, Wonder Woman can punch harder than Superman. And they're considered to be in the same class. And some of these problems are quantum factorization. So factorizing numbers is essential for encryption, to break encryption. And quantum computers are exceedingly good at that. If we had a big quantum computer, you could break all the codes in the world and steal all the money and so on. It's going to be many years before we get to that. And we're going to have quantum encryption, which is way better anyway, and we're going to be all fine. But this is the kind of like, these are the things that sell the whole field. These are the kind of problems, like a big promise of large advantages over current algorithms. And this is more like, if you have a big problem, talk about alien invasion on planet Earth, you need Superman on Wonder Woman. Batman, you know, he's all right. I like him a lot, but he, you know, for these things, you definitely need Superman, Wonder Woman level power things. And factorization is one of them. Another one is quantum chemistry. Quantum chemistry, if you think about it, it's a little bit like a network of electrons, right? And these electrons are quantum mechanical, and they're connected in quantum mechanical ways. And it's actually quite hard when you add one more electron, you want to calculate the energies, you want to calculate the structures. It is a really hard problem. And quantum computers are exceedingly good at that. So this is also a Wonder Woman level problem. However, there's also some easy problems in quantum chemistry, like finding the ground state of a molecule, finding the lowest energies, and so on, that are a little bit easier. They don't get super advantaged like here, but there's some other problems that quantum computers are good at that seem pretty darn powerful, just not at this level. And these ones I'm calling like Aquaman level problems. You know, Aquaman, he's the king of the seas. He can talk to fish, all that stuff. And so a lot of people make fun of it because it's not as powerful as Wonder Woman and Superman. But Aquaman, if he's in the water, he can actually, he's almost as powerful as Wonder Woman and Superman. But he has to be there. Like, it is for some problems, he's really darn good. Outside, not so much. And then we have some other problems. There's a whole class of quantum machine learning. And nobody knows where to place this because machine learning is heuristics. That means whatever works. That's what heuristics means. And so it's a little hard to compare the complexity. And so people don't know where to put it. There's a lot of experimentation to do. So if you really want to do some cool stuff, just running code, you can run classical machine learning codes, quantum machine learning codes, and try to compare how they do. For example, there's and nobody knows where it is. It could, some people think it's here, some people think it's almost here, and the most likely thing is going to be very good for some things, and for it's going to be at this level for some things, and at this level for some other things, and we don't know. And this has to be done by experimenting. And I am representing this by John Jones, also known as the Martian Manhunter. He's also part of the Justice League, and because he's really powerful, but nobody really knows for what. Superman has said he might be as powerful as Superman, but we haven't seen him do anything that useful. But sometimes he is, so we don't know. We have to see him in action more, I would say. Yeah. And then finally, I'm going to introduce one last superhero, And this one is the one I refer to as like quantum supremacy. Quantum supremacy was claimed by a team at Google 1 year ago. They have a quantum computer that they claim achieved quantum supremacy. Quantum supremacy is that you have a quantum computer that can solve one problem that any big classical computer right now could not solve. That is really what it is. So it is like you beat, like one quantum computer beats them as faster at something than anything you can achieve with any classical computer. Of course, it can be any problem. So what they did, the Google team did, is like, they came up with a very, very, very clever problem that their quantum computer that's very noisy and has all the other things that's really good at. But it's very useful problem, it's like touching your nose like this, like, yeah, you can do it, but what for? But of course, it's a very important proof of concept, because if you achieve quantum supremacy, and they did, that means you are definitely in the superpower regime. You're not talking about Batman stuff. You're talking here, Batman has no superpowers. Here, you're already superpowered. Maybe not so superpowered, maybe it's not so impressive. But definitely superpowers exist at that point. Even the biggest deniers, they would not. This is a proof that they were wrong about this. And I'm representing this by this superhero here. He's called Stone Boy, and he's often proclaimed the most useless superhero in all the DC universe. And it's because his superpower is he can turn into a stone statue and not move for 6 months. So if you're going to a fight, alien invasion, or you have to do something, he just stays there and does nothing. And that's all he does. Is he superpowered? Absolutely. Like, there's no doubt about it. I much rather have Batman because it's kind of more useful, but definitely Stone Boy is superpowered, Batman is not. And that is kind of the point of this experiment. And what we will see is we're gonna see more and more algorithms, more and more computers trying to push it out of this proof of concept that this quantum powers exist to getting it to some useful small thing. This is where the things are going. So I want you to now go look at this example. It's called roll with the demand. Let me show it to you here. Okay. So it's this one, roll with the demand. And this one it's a long read. I just want you guys to take your time with it. I'm gonna set up the problem a little bit. So this is an optimization problem that it's actually quite common problem. It's a very difficult problem that quantum computers seem to be better at. So the challenge is imagine that you have a limited supply of something. In this case, I chose toilet paper as the example. You can guess which time of this year this was, when everybody in the world was like they couldn't find toilet paper. Okay, so the idea is like you have a limited supply of something and there's a very high demand, and you have some markets, some stores, some places to store it. So they will be like this. But you do not have enough time to every day supply all the places. There's just not enough toilet paper or not enough trucks or something. What is the best order to supply them such that people don't get frustrated and freak out because they cannot find toilet paper? Okay, so this is an optimization problem. It's how to do it. And this is known as the max cut problem. And the way it works is the following. It's like the mathematical way is, for example, you could say, on one day, I put things on this market only. All the toilet papers on market 0. On the other days, I distribute it among all these. For example, this might be an option. However, this one is not so, as this problem is set up, this is not ideal, because if the person happens to go to this store, they're not going to find toilet paper. Then they go to this one, they're not going to find toilet paper. Then they go to this one because they're neighbors, they're not going to find toilet paper. And by the time they make it to this, they're already frustrated and freaking out. The owner of the world is coming, we all went through this. So there's clearly better ways to do this. And mathematically, what you do is like you have to cut the network. You have to find a good way to cut this network through it. And you want to cut as many of these connections, as many of the neighborings as you can. And if you do that, this will give you a way to do, optimal way to do it. For example, a better cut is like this. If I do one cut like this, and let's say on odd days, I give toilet papers to these 3 stores, and on even days, I give toilet papers to these 2 stores, and so on. I take turns between them. This is more efficient, because even if no matter which one you go, it won't take you so long to find a neighboring store that has toilet paper. And there's a lot of options. One has to try many, many options to do this. And there is a quantum solution for this. Oh, I think I have to fix this clearly, but I will show you where this is in the library. Yeah, so okay, here, give me 1 second. This is in here. Yeah, so okay, so this is in the library here. Yeah. Okay, so this is the same thing. You can add this project, and you can run some code that will do a quantum algorithm to try to solve this problem. This is really what it does. This is clearly a useful optimization problem. And by the way, applications to this is not just for logistics, but this is very important also for finance, because this is the idea that you have a lot of risk tied together. How do you break the risk so you can hedge? So you like, you know, like, oh, you're scared the end of the world is coming. You put all your money, you spread out your money too much. How do you start saying like, I'm gonna sing? How do you do it so you play safe? So you want to bet something is gonna go up. You want to bet on some things that are gonna go out. So this is the algorithm for that, and this is one of the options for the cuts, and that you can do is a cut that goes from cuts 11011, and the explanation is here what these cuts mean and so on, the interpretation. So I just want you to run the code and like look at it and just play with it with some realistic example. And there's some other examples here as well that you can use. Okay, so here. Okay, so this is just to show there's some concrete examples that have some applications for some things. Okay, so kind of to conclude, this is where we are in quantum computing. Quantum computers are big, unreliable machines with vacuum tubes almost. We got to think vacuum tube era. We don't have the transistor yet. And back then, with the first computer, this is the ENIAC, if you wanted to code in it, you basically had to beg for access. You had to like go knock doors, please, 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 I want to connect this thing. And half of the time it wasn't working right. The other time it gave you a lot of errors and so on. So so this is just this is where things are now. And I would say like that right now. Well, imagine if back then a lot of people will have had access. It wasn't begging. It wasn't. People could start playing. They could start testing the technology. Imagine how much faster computing will have developed. So and I think this is you guys. This is really what you're doing right now. You're part of these people that are playing. So in part of quantumcomputing.com, now you have an account. You can play with code, of course. But you know, as part of your account, if you want to implement some quantum algorithms that are out there, show some examples, then you can put them here. This is an open source community. You get full credit. You can have your name here, your picture, all the algorithms that you have. And then if you do a cool one, share with me, send me an email, and I'm happy to add it to the library. We are still in beta. We haven't launched yet. We're about to launch. But right now you see everything here is by Strangeworks. That is me. We have a lot of partners that are going to be putting a lot more content soon. And we would like this to be a thriving community of people that just want to play and learn and implement things and share them. So if you guys want to be part of that, please, you have an account now. You just go crazy with it, and let me know. And I'm happy to add stuff to the library. This is no problem. We want a thriving community. And then the other aspect this is of course the community aspect is very nice and so on, but we need to do stuff to pay the bills. So the other stuff that we do is in Strangeworks, we have a sort of a solution for big institutions like a big university or HPC centers, where we also offer quantum access to all the hardware that's out there. Basically, we have partnerships with all these, and we don't make any money off hardware sales. We just do all the management of all the software to get it all running in one place. And we understand that big institutions, you need like teaching tools, which is the one that you saw today. But we also have management for the hardware. This is for the more administrators. And we have full SDKs and so on for like real research, not just the typing in the browser. There's a lot more stuff, but this is the stuff that pays the bills. And we think like with such a solution, this is really good there has very good things for students, for teachers, for researchers, and organizations. So once again, thanks a lot for paying attention. If you have any questions, now is the time to ask. You can find me on. You can send me an email anytime you have any questions, or if you do something cool in our platform, or you find bugs, please send me an email if you find bugs too, because we have a launch. I will love some help. Thank you, guys.
Thank you, Cesar, for the super nice presentation. If there's questions or if you just want to stay here while trying out some things and you might have questions later, then
yes, I'm very happy if you guys play some more and you have some questions. Yes, absolutely.
Yeah. Yeah. And we can leave this open until, I don't know, 10 more minutes, for example.
Yeah, and
in case people have questions.
I forgot to show something in the platform, so I will take that time to show it because I think it might be of interest. Okay, so all right. So when you create a project, you can import from Git repositories like GitHub and so on. You can put the link here, and so this means if you find examples that are open out there and you just want to try them in the platform without all the headaches of getting all the libraries to work, by all means put it here. And if something doesn't work, also let us know, because sometimes we're missing libraries. It's impossible to have every library, but we're aiming to that. So feel free to go look up code online, try to run it here for the different platforms. And another way you can start projects is, of course, we can use some of our examples as a starting point for them. And finally, I want to say that if you want to create a project from scratch, you can do that. And let me show you all the things that you can do. You can have just plain Python notebooks. These are Jupyter notebooks. They work in the platform, Chasm, but we have support to all this platform: Forest, PennyLane, Zurich, Cascade, Bluecat, Q#, Ocean, Amazon, Project. These are all places that we support, and we're gonna keep adding more and more and more. You're gonna see here, and of course we have the hardware access for the. That one's not free because we don't have enough money to buy our hardware access. So that's a big commitments that are needed by big institutions. But if you want to play with other things, and if you notice in the library something is missing, and you want to contribute, for example, we have some examples from languages. If you want to give your try it and do it in Project Q, let's say, and write the code for the entanglement one or so on in another language, feel free to do it, and you let me know, and we'll put it in library. You get the credit. It's gonna be your name here, and we're gonna thank you very much for contributing. This is like a good exercise to get started in programming languages in Quantum. It's just try to translate stuff or try to get examples from others running. Yeah.
Are you hiring anytime soon?
I cannot say yes, but hopefully soon. Yes, I can say soon. Yes. Yeah. And for that, our company is a bit different than other quantum startups because we're a bit more heavy on the engineering team than the science team, and this is on purpose. We see ourselves as doing all the infrastructure work that the physicists don't want to do to get this stuff running. And so I'm a physicist. I'm part of the science team, and we are planning to grow the science team and the engineering team, but not yet. Like, we cannot make any official announcements yet, but stay tuned, please. Yeah.
I had another question,
Mm-hmm.
namely about the QUASM language. Is it like a standard that is used by all the big companies, or?
Yeah, that's an excellent question. It is a standard. Now there's a little differences between them, but people are trying to keep it as the standard. It's not used by all the companies though. There's good reasons for that. Is that it is a standard for one kind of quantum architecture. For some other architectures, it just doesn't make any sense. But for the main one, it does. And most of the languages, they try to write to Chasm, not all. Most of the hardware are trying to support Chasm. And the ones that don't have it, they're doing it. So it does seem like it's becoming like the standard one. It's so early that it's hard to know, but for sure you will run, if you try to run anything, you will run into a lot of Chasm always. Like, this is really a main one, which is what I focus on, that one. The Qiskit, the IBM language, is basically a Python wrapper on Chasm. And Zurich, the Google one, it's a Google Python wrapper on that one, and so on. So, but if you understand the tools of Chasm, you will see it like coming along up. And with that said, it's evolving very fast. You saw the example that we have is Chasm 2, and they're gonna have a Chasm 3. It's gonna be released at some point with a lot more things. I can tell you that I ran some stuff on hardware on Rigetti, and we were submitting code to Rigetti hardware on like 5 different programming languages because it took Chasm. So we could do that. It was really cool because you're programming all this language in the same hardware, but it's really because it accepts the same intermediary code. So it's almost standard for some things. Yes, that's what I would say. Yeah.
Okay, thank you. And also the quantum hardware this is designed for, is that like superconducting circuits?
So the Chasm is intended for gate-based quantum computing. The main ones for that are superconducting qubits and ion trap computing. They're both using the same model. There's other kinds of models. There's quantum annealers that they do not use that because it's just annealing is a different thing, completely different thing. And there's a continuous variable computer, which is use photons and light and so on. And for those, they don't quite use even qubits. They use quantum modes and other things. So it's not appropriate for those. So it is used for everything that uses gates and circuits and so on, which is a very big class of quantum computers, but it's not the full thing. Absolutely not. So the hardware is really diverse right now, and I think it's going to stay diverse for some time, and that's a good thing. Like we don't know which one is going to win, and that's okay. That's why it's exciting. Yeah.
Thank you.
All right, so if there's no more questions, then we can thank César again, and hope to see you again soon.
Yes.
So maybe in the next semester, we'll have another course.
Yes, and please, guys, send us a lot of feedback because we're in beta and we really could use some feedback. If something doesn't work, please, like this is really what we're all I'm asking from you is like, please give us good feedback. Tell us what you like and especially what doesn't work or what you would like to have, because we're very small this time and we take this field very seriously, so we can grow it the directions that you guys find useful. Yeah.
Very good. We will send you feedback.
Okay.
Okay.
Bye.
Ciao. Bye.